Right. I think we are all set to get started. So, for today's session, which I want to start with, is a few feedback and questions that came in from the nanolog session, which was the first session of the reading group. I thought I'll just go over them real quick so that everyone's on track as to what's going on in the background to make these sessions even better. So, starting off with, there was one feedback about more sort of hands on. So, these research papers obviously are very theoretical. They do give a taste here and there of practical stuff, but it's mostly just words and kind of giving you the intuition of what's going on. So, to make things more hands on, what I've decided is that for Sieve, which we'll be discussing today, there will be a separate session, probably sometime next week. I'll put up a poll for that soon, where we'll be live coding Sieve with Go. And as part of that session, we'll be starting from scratch, like a blank file. We'll implement Sieve, we'll run it on a few input traces, and we'll actually see how it performs. For the nanolog session, I know the 2 sessions for nanolog are done. They weren't recorded because that was like a sort of the first time that this reading group was happening, and it wasn't very clear how popular it would be. But with the traction that it has, I feel that there is a chance that we can go back to nanolog and try making a proof of concept for it. The reason why I say proof of concept is because nanolog on its own is quite vast in terms of what it's capable of. So if we can make a simple proof that, okay, if you play with a small Go program or a small Rust program, that you can build nanolog in a certain way, that would still go a long way in making things clear to people as to how you can implement what you see in papers. Because one of the main motivations of these sessions is to not just explain papers to you, but also to motivate you to go and say that, okay, now I understand the paper so well that I can try implementing it in my favorite language. So to make that more clear, this is something that will be happening soon. About session topics, there were a few questions that came to me on DM about what topics can be discussed in these sessions. So I have a list here of topics in general, which if you have a paper, a blog post, or even a conference video, and you feel it's something that we can cover in these sessions, please feel free to share them either on the channel or share it with me directly if you're not sure if it fits the topic well, and I'll be more than happy to help out. On the bottom, you can see I've mentioned AI/ML. I'm not very certain how popular that will be. So if you have something very specific, which is sort of related to systems or some domain that crosses between the two, please feel free to share it. And in general, if you're not sure about something, just ask on DM. I'll be more than happy to give you some direction on if this resource is something we can cover in these groups or not. And yep, the final one is something I mentioned earlier as well. So quickly glossing over that this session will be recorded and you can view it later for reference. And if people aren't there in live, they can come back and watch it later. These sessions are normally an hour, so the video will be just as long. With that, as always, keep providing questions, any doubts or suggestions that you have, either on the Discord channel or via Discord DM. That always helps in improving the experience for everyone, and it just makes these sessions better and better. So with that quick update, we are all good to get started on the Sieve way of cache eviction. So the interesting thing about Sieve and especially cache eviction is that though in university or when we read about cache eviction policies, it's a very brief discussion that we tend to have with people. You know, there are certain algorithms which we know about, like one very popular one is LRU. People keep getting questions on that to implement. There is MFU, which is most frequently used, or MRU, most recently used, and so on. So we throw all these acronyms around, right? And this field is like decades old. It even was there before the 2000s. And people have been trying to improve the performance of caching over time because of how important it is to our daily applications. It's in a way very hard to think of any application in your life where caching is not used. Any interaction with a website, any interaction with your file system on your computer, with your code editor, or anything like that, there is some caching somewhere. Caching also, in a way, you see it with your comparative programming problems. People will know it as dynamic programming, memoization. That's again caching. So with all of that, it's important to kind of look at caching in a holistic way. I just want to go over this real quick to give everyone a level understanding of what is expected from knowing caching concepts. So in general, when you think of caching, especially for today's session, just think of it as a black box, which we'll be exploring further. where you give certain requests for certain data, and the black box will give you back that data if it's present. So this is important because sometimes that data may not be in the black box, and in that case, you'll have to create that data or calculate that data on your own. The other point is when you think of caching, right, it has two main components. One is something known as the storage, because obviously caching has to manage the storage you give it, right? For example, when we talk about CPU caches, we talk about a 10 MB cache or a 5 MB cache or a 16 kilobyte cache, right? There is some space that these caches have, which they use for holding items for future use. And the other component is the eviction algorithm. So the eviction algorithm is like the manager, where given a storage, the eviction algorithm will say, okay, I need to manage this storage so that the objects I keep are something that will be used in the future. And frankly, the best way I feel that you can understand this is by looking at this visualization here, where the eviction policy is all about throwing items which are not valuable or it believes are not valuable. And we'll explore that further in today's session. And it keeps certain items which it thinks are valuable. And as I said here, it thinks that they are valuable. Sometimes it gets it right, which is a beautiful thing. And that makes your applications faster. And sometimes it gets it wrong, in which case you have to recalculate data, which is expensive, and that can slow down your application sometimes. Another interesting point, which I just want to touch upon, and I feel it's something to think about even after this session, is that the concept of eviction only exists because you have a finite amount of space to deal with. If you had infinite memory, or you knew how much data you need to hold, you could actually do away with an eviction algorithm. You can just say, whatever data comes, I'll hold it in my storage because I have enough storage, and whenever you want the data, I'll give it to you. So then the whole eviction discussion goes away, and Sieve becomes, or even LRU becomes pointless. But in most practical applications, that's quite rare. So that's why these algorithms still are a very rich research space, even today in 2024. Another point which I want to touch upon real quick is web caches, because if you see the paper title for Sieve, it's actually called a cache eviction policy for web caches. And this is a very interesting term because this is a particular domain of caching, right? This is not every type of caching is a web cache. That's not true. So specifically when we talk about web caches in today's session, we are mainly talking about two things. One is CDNs, which people who have worked with front end, who have deployed websites would have heard about. And then there are key value caches, which people who have worked on, backend applications which are in production, they would have seen these type of caches. So I'll cover these real quick to make the points clear and give that level foundation for everyone. When we talk about CDNs, right, we are mainly talking about delivering certain static content to end users such that it's faster for them and it occupies less bandwidth. So by faster, I mean that it takes lesser time for the data to reach them. And that's by geographical time, by geographical distance, I mean. So you can see an example here where if Google were to serve you their website from the US, it would take much more time for that data to reach you sitting in India. But given that Google does have their website and servers hosted in India, I believe in Mumbai and so on, they can actually serve that data to you much faster. So the time taken is much lesser. So all the images of Google and the Google icon that you see on the search bar, that's all coming from a server that's very close to you. Another point is bandwidth. And this is something which I feel is sometimes tricky to describe, especially why do CDNs reduce bandwidth. So I came up with this visualization to help make this more clear, where you can imagine that there are 3 countries, A, B, and C, and they all have a bandwidth or a network line going out of the country to connect to this country D, which you can imagine is, say, Singapore or the United States, where many companies have their servers, right? Google, Amazon, Microsoft, so on. The interesting thing is that if all these countries send their bandwidth out, right, which is I've marked here as N, this single link here would need 3n bandwidth. It would need 3 times that bandwidth to send all that data to country D. And this is a very realistic thing. This is not a contrived scenario. You can imagine all your undersea cables, your transatlantic cables, your trans-Pacific cables. All these cables are very few. You can actually count them on your hand. And when you have so few cables, you need to use that bandwidth very frugally. You need to be frugal with these things. And that's what's happening here is you're not doing that, right? You're sending all your bandwidth across these cables and you're just overusing things. When you have a CDN, what you can do is you can have a CDN in every country. So one in every country A, B, C, and a lot of that traffic can be handled by the CDN itself within the country. So the data that's going out of the country for those requests that leave the country because the data is not in the CDN is lesser now. And because of that, the data you need on that cable link, which is that transatlantic cable, trans-Pacific cable, all of that is much lesser now. So you're using your bandwidth much more frugally because you're sending the data much closer to the user. So the request that they send travels much lesser in terms of distance, it travels in fewer cables, and that frees up space on those cables for other requests. So that's the whole bandwidth play that happens with CDNs. And finally, we have key value caches. So key value caches are very simple. Imagine you have Twitter, right? And they want to give you the count of likes that your tweet has. Now, this operation, right, of finding the likes for a tweet can be expensive because when you need to find the likes for a tweet, you need to find who has liked your tweet, get the count of those users, and then return it back to the caller, right, to the person requesting this number. And this can be an expensive operation either in your database and whatnot. So what you do in your key value cache is you just store that for this tweet ID, this is the like count. So when the user sends you a request that, okay, what's the like count for my tweet? It just hits the cache matches the tweet ID, and it just sends back that number, which is the like count for your tweet. And that's it. No extra computation. Your backend is not overloaded. No extra database calls, nothing, right? It's all done in the cache. So this was the sort of overview of cache that I just wanted to give everyone for a level foundation so that we're all on the same page. And before moving forward with Sieve particularly, I wanted to also talk about the caching landscape, which I feel is very well covered in the paper. So this is mainly something that the paper covers in terms of types of caching algorithms that exist today. And they fall into three main buckets as the paper describes them. One is LRU style, which is the oldest style of caching, like LRU, FIFO, and so on. There are others which are multi-LRU queues. So you can imagine there are multiple queues which hold objects, and each one has its own LRU setup running. And finally, you have machine learning. And for people who are a bit surprised, that is true. There are algorithms and papers that have come out recently on using machine learning for caching. It's quite an interesting space. And there are some algorithms which have also been used in the paper for comparison. But it's quite interesting to see that machine learning is being used here as well, because normally machine learning is known to be quite resource heavy. Inferencing can be slow. We have all seen that with generative AI models, that it's not always fast and it needs a lot of hardware to run quickly. So that was an interesting space. But for today's session, Sieve is much similar to LRU in simplicity. It's actually simpler than that. So we can all be happy and it won't be complicated, the explanation in this session. So when we talk about Sieve, mainly there are four categories in which the authors have talked about Sieve, and I'll describe Sieve as I go through these categories now. So number one is simplicity. So Sieve is supposed to be a very simple implementation of caching eviction policy. It's supposed to be even simpler than LRU that we have all learned in university. So the reason why this is actually very good is because in case of Sieve, when things are simple, people tend to implement those algorithms more in production. And they even provide evidence of that in the paper, that if you see any of your famous caching libraries or caching products today, whether it's Redis, ATS, Varnish Cache, or Nginx, which are names we have all heard of, they all use FIFO and LRU, which are decades old algorithms, right? So you can imagine that these companies and these groups who are working on these products have just ignored all the other algorithms that have come in between from research because they were too complicated. Another point is, when you think of production, especially people who are in industry, you'll know that when things are simple, it's easy for you to maintain that piece of code. It's easy to scale that code. And it's also easy to debug it, because when your code is doing less things, it's easy to find out what's going wrong and eliminate certain possibilities. So Sieve actually does play very well on that. Another one was efficiency, which is something which a Sieve does perform very well. It even beats LRU. And I'll come to these ratios a little later, because once we see the algorithm, this will make a lot more sense. Finally, which I wanted to cover was scalability, because this is something which Sieve does talk about a lot in terms of when you have a cache, normally that cache is shared amongst different threads. So, for example, if you have a cache for your website, right, that cache is not going to be just for one thread or for one request. It'll be shared amongst requests that come to your website. So, what that implies is that you're sharing that cache amongst multiple threads. And when you're sharing amongst multiple threads, people who have done multi threaded programming know that you need locks or you need some atomics or you need something like that, right? Otherwise, you'll have race conditions and so on. So, the thing about Sieve, which makes it very powerful, is that it doesn't need locking simply because it just accesses one item in the cache and it doesn't need an entire lock on the whole cache. It just does one atomic operation when accessing the cache and that's it. It doesn't need to lock the cache because it doesn't modify the cache at all. So I will be doing a demonstration later in this session where we'll be comparing FIFO, we'll be comparing LRU and Sieve all next to each other on a certain trace. And there it'll be more clear that in case of Sieve, you don't need locking of the entire cache. You can just atomically access one item in the cache and you're done. So that makes it very good when you're having multi-threaded web servers and caching setups, which is very close to what you have in production today as well. So with that, there is one, so there's one thing here when you talk about Sieve, right, is the setup in terms of Sieve is that when you need to store data in your cache, not all of your cache is going to be used for storing data that you allocate. So for example, if you take 1 GB of space and you give it to your cache, say you're using Redis, right? You take Redis, you give it 1 GB of space for caching. The reality is that you can't store 1 GB of data in your cache. It's going to be less than 1 GB. And the reason for that it's less than 1 GB is simply because if I delete this, you'll see this underneath, which is bookkeeping. So this is something which in the Sieve algorithm, you just need a few bytes to use to have your bookkeeping. So I can show you that over here in this section. So in case of Sieve, what happens is that you have a doubly linked list which stores your items in your cache. And when you have a doubly linked list, what happens is for every object, you have 2 pointers because you need a next pointer to the next item in the linked list. You need a previous pointer to your previous item in the linked list. And in Sieve, there is 1 bit that is used for storing whether the object has been visited in the past. That means a cache hit, or it's not been visited in the past. That means it's not been used. So what happens in this case is you have 8 bytes because we are using a 64-bit system, so pointers are 8 bytes. You have 8 bytes for the previous pointer to point to the previous node. You have 8 bytes for the next pointer to point to the next node. And you have 1 extra bit to track the visited status. And this 1 extra bit takes an additional byte because we know that CPUs are byte addressable. So if you need an extra bit, you need the entire byte. Unfortunately, so 7 bits are wasted, but you need that extra byte to store the metadata. And this is Sieve's overhead per object, that it needs to store 17 bytes of data per cache object that you store in it. And this is the data structure of Sieve, that it's a doubly linked list where you have, for every object, you have 2 pointers, previous and next, and you need 1 byte for storing the visited status. Now, before I move further, I just want to pause if anyone has any questions about caching or the data structure of Sieve. I've not done the algorithm yet, which I will be doing now, but in the data structure or the caching concept, if anyone has any questions, feel free to unmute or write in chat. I'll just wait for a few minutes if anyone has any questions. Mainly what we have covered now is just the introduction to caching, a few caching concepts that everyone's on a level feel, and the data structure for Sieve, where it's a doubly linked list and every item in the linked list has 1 extra byte for storing its visited status. If everyone's clear with this, feel free to write yes in the chat, or you can even react. I think on Discord you have these emoji reacts as well. If everything's clear, feel free to let me know, then we can continue forward on to the algorithm. Perfect. Okay, that's perfect. So that's great. So we're all here till now. So now what we'll be talking about is we'll actually be going over the algorithm for Sieve. So what we're going to be doing now is we'll be taking a trace. I have the trace. I'll just slide on to that in the whiteboard, and we'll be going over that trace with the Sieve algorithm. And we look at the number of cache misses that you get, because cache misses are very important, right? We need to reduce the cache misses as much as possible. And then we'll be running that trace on LRU and FIFO, and we'll be comparing the values, and we'll be seeing that Sieve performs better. So this way you'll not just see the algorithm in action, but you'll also get to see that it's more performant than say LRU or FIFO. And it's also quite simple. So enough of hyping up the algorithm, let's actually get into it. So here we are, right? So this is the section that I have. So this is the input trace. Many people who have had, I guess it was operating systems. Yeah, I think in operating systems, you normally have these questions where you're given an input trace and you need to go over that input trace and see what is the cache miss and stuff like that. So this is our input trace for today. These are objects. Basically, there are integer values. I've just kept it simple with integer values. And we have a cache of size 4. So you can see this here. Our cache is of maximum size 4. And we have these input queries coming to us. And you can see I've got this set up already for Sieve, LRU, and FIFO, and we'll be doing it for each one so that we can compare the cache miss count. And that way we can be satisfied that, okay, what this algorithm is and how it performs. And what I have here on the right is the algorithm for Sieve itself. I've taken this from the paper. And for people who are wondering, this is literally the entire algorithm. It's not even 20 lines of code. And what I'll do is I'll go through this real quick so that we can then apply this on the example and we can have much more clarity on how this works. So looking at this algorithm, right, what you have is essentially a few components. One is you have a request X. So request is basically you're requesting the cache for some data. As I mentioned above with the black box example, right, you're requesting the cache for some data, which we call X. Then we have a doubly linked list, which, as I mentioned, is the data structure that we use for Sieve. So that's what we call T. You have your cache size, which for us today in our example is 4. And you have a thing called a hand. So the concept of a hand will be much clearer when we do the example. But just remember that there is this pointer. It's literally a pointer, which is called the hand with the variable P. So the way it works is like this, that the happy part is that the item you're asking for is in the cache. That means it's in the doubly linked list. Then it's very easy, right? You just mark the item as visited. That is that extra byte, that extra bit I was talking about, sorry. You mark that as 1 so that your setting saying, yes, this item was visited, like it's a cache hit. And you're done, right? You find the item in the cache, you mark it as visited, and you return back. As easy as that. When there is a miss, now the specialty of Sieve comes in. If there is a miss, like any caching algorithm, the thing that you'd want to do first is know that does the cache have any free space, right? Because if the cache has some empty space, I can just put the new object there. I don't have to disturb any of the existing objects. And that's exactly what we do in Sieve as well. So you can see that if the length of the cache is equal to C, then we do what's in this body of the if function. But if it is not equal to C, which means that there is some free space, you can see on line 15, we just insert the item into the cache, into the head of the cache, and we mark the visited as 0. So the reason why we mark the visited as 0 is that in Sieve, we only look for a cache hit when the item is in the cache. So remember that when we insert a new item in the cache, it was not there in the past, right? That's why we had a cache miss. So that's why the initial value is always 0. If the item is in the cache, like in the cache hit case on line number 2, and the item requested was a cache hit, then we mark it as 1. So the concept is just that if the item is in the cache and it was a hit, we make it a 1. If the item is coming from outside into the cache, we set it to 0. We initialize it to 0. That's on line number 16. Now, the third part, which is the third case, is that the item is not in the cache, and unfortunately your cache is full. So what that means is that you need to empty your cache, right? You need to throw something out, you need to remove something which is unpopular, and you need to create that space for your new object. It's as simple as that. Every caching algorithm does it, but the main secret sauce of every caching algorithm is which item to throw out, right? Which item are you going to remove? So the way that Sieve does it is like this. If the size of your cache is C, which means that your cache is full, what you're going to do is you're going to start at where the hand is. So the hand is P, which you can see here as this arrow. I'll be using this in the example as well. You start at this pointer where the hand is, and what you do is that if the pointer has reached the ends of the cache, right, because it's a doubly linked list, you may reach the end of the linked list. You just wrap around. So if O is null, which means if the pointer is null, you just restart back at the tail, that is one end of the cache. And that's line number 6 and 7. Essentially, that line number 6 and 7 is telling us that if you reach the end of the cache, you need to wrap around back to the other side. It's just that. On line number 8, what we are basically saying is that if the item that we are currently on, which the hand is currently on, is set to 1, that means it was a cache hit in the past, then we make it as 0. So we are resetting the value to 0. So by resetting the value to 0, and this is also how the authors put it, you're marking this item for eviction in the future. So what you're saying is that this item was a hit in the past, that's why it was set to 1, but it may not be needed in the future. So for now, we're just going to set it to 0. We're going to set the value of visited to 0, and we proceed forward. So on line number 10, you can see that we say O is equal to O of previous. So we actually move through the cache. We move to the next item in the cache. And again, on line number 11 and 12, people with keen eyes will notice that we are doing exactly what we did on line 6 and 7. And the reasoning is the same. If you reach the end of the cache, you need to wrap around back to the other side, because you need to continuously scan the cache until you find a free item or an item to evict. So again, if you reach the end of the cache, you wrap around back to the other side so that you can evict items. You can scan the items again, essentially. And finally, on line number 13, right, which you can see is outside the while loop. When you're outside the while loop or you have come out of the while loop, you would have come to an item where the visited is 0. Because we can see on line number 8, right, that if the visited of the item is 1, then you're going to stay in the while loop. But if the visited is 0, that means that the item is possible for eviction. You can actually evict it. So we come out of the while loop. And here on line 13 and 14, what we're just doing is we are removing that item from the cache to create that free space. And then on line 15 and 16, we are again inserting the incoming item, which was a cache, which we had missed, right? So we created the space in the cache on line 13 and 14. And on line 15 and 16, we are inserting that new element into the cache. So this is the Sieve algorithm. This is what these 16 lines of code are doing. An easy way to remember it as we go through the example, and I will pause for questions now, do not worry. Before we start the example, I will pause for questions, but I just want to mention once again that all you're doing in the cache is that if you get a cache hit, you're marking a bit as set, which is the visited bit. If you have a cache miss and there is space in the cache, then you just insert the item into the cache because there is free space. We can accommodate the incoming item without any worries. The third case, which is the important case, is that the cache is full and the item is not in the cache. So we need to create space now in the cache for this item, right? We need to accommodate it. So to find that item, which we need to remove to create that free space, we are scanning over the cache and we are searching for some item whose visited is 0. And we remove that item whose visited is 0 and we put our incoming item there. That's essentially what this algorithm is doing to handle those three cases. And yep, I will pause for questions now. I know there might be many. Feel free to unmute or write in chat. Before we start the examples, we can go over the questions on the algorithm. Yep, you can go ahead. Before we start the example, I'll just wait a minute. I just want all of you to see the algorithm that you see on your screen, just to internalize it. And um, if you have any questions, you can ask it now before we start the example.
Yeah, I have a question.
Sure.
Am I audible?
Yes.
Okay. So this my question is regarding when the cache is full,
Mm-hmm.
and we are iterating over through the elements in the data structure, and I just wanted to reconfirm that if we get to the items who are already visited, we'll mark them as unvisited and then move on to the next one, right?
Yes, that's correct.
I mean line number 8 and 9. Yes.
Exactly.
Okay.
Yeah.
Okay. Okay. So we'll eventually get to a point where we'll definitely find something that's unvisited.
Yes, that's correct.
Okay.
So just to expand on that a little more, um, one point that we need to remember is that from line number 8 all the way to line number 12, right? That is all the while loop. And if you see, the while loop will keep going through the cache. It will keep scanning the cache from start to finish, until it finds an item whose visited is 0. And a very interesting question you may have is this eventually going to happen? What if the loop goes into an infinite loop? Which is always a good question to ask. So the answer is that the loop will not become an infinite loop, simply because if an item's visited is 1 in the current scan, say scan number 1, the item's visited value is 1. If you notice on line number 9, we are setting it to 0. So when we come around the next time, when we do the next scan, that is round number 2, when we come to this item, its visited value will be 0. And when its visited value is 0, we will break out of the loop and we will discard this item. So this while loop, which you see from line number 8 to line number 12, it will eventually terminate.
So let's say initially if all the items have been marked as visited.
Okay.
So in that case, I think the worst case complexity would be like it will have to go through all the nodes in the linked list, right, to find the first item to delete.
Yes, that is correct. It will have to do one scan to mark everything as 0. And in the next scan, the first item it will find will have visited as 0, because in the previous scan it set everyone to 0, and the eviction will happen. So after n items, the eviction will happen on the n plus 1th item.
Got it. So in this is the worst case where it will have to go through all the items. Otherwise, usually it might find some unvisited items even before completing the entire loop.
Yes, that is correct. If people are interested in knowing it in asymptotic complexity, you can think of it as the worst case is definitely O of n, because you have to go through the items, I mean, all the items in the cache once before you find an item that you can remove. But the average case is definitely closer to n by 2, or half, because it's going to be very rare that all the items in your cache have visited as 1. It'll be possible that some item in between has it as 0, which you can evict and um, make free space for the incoming element.
And one more thing, like this, the hand pointer, does it always start from the tail when it's searching?
Okay, that's a very good question. So the hand pointer, initially when the cache is created, it starts at the tail, but after that, it will keep moving forward to the head, and across different scans, it will just stay at its last position. So to make that a bit more clear, you can imagine that when you inserted the first couple of items, the hand was at the tail. Then you needed to evict something, so the hand had to move somewhere in between the cache, and after that, the hand will stay in between the cache. It won't reset back to the tail. you can imagine that the hand has its own state. It'll just stay wherever in the cache it last was. It doesn't reset any time to the tail. It just keeps moving forward to the head and then wrapping around and, in a loop.
Got it. Thanks.
I'll just wait 1 more minute for questions. If you have any questions, feel free to ask. This algorithm, I know initially is a little bit surprising because of how small and simple it looks, but to internalize it is very important so that in the example things will connect a lot better. So if you have any questions, any small doubt clarifications, also feel free to ask them now.
Yeah, hi. One thing here, I want to discuss more about what's the intuition behind this algorithm. I think the algorithm is sort of easier to understand, but yeah, regarding intuition, if you'll be covering it later, then we can have the discussion then. But yeah, I have a few things to discuss, a few questions there on the intuition of the problem, why this algorithm is the way it is.
Right. So the intuition I will cover after the example. If I have to name drop a single line here, it's essentially lazy promotion and quick or eager deletion. So essentially here we are being lazy when we are promoting items, and I'll explain that laziness better when we get to that after this example. And we are being eager in throwing items out of the cache because again, I'll just mention one line on this, is that when you talk about web caches, right, generally items are not very popular. Most of the items are quite rarely accessed. There are only a few items that are very popular, very much accessed, very hot items. So for that reason, throwing things out of your cache eagerly and promoting items in your cache for a long time lazily actually works very well. And this algorithm embodies those two concepts.
Yep, got it. Yep, you're on point. Let's discuss more about this later after the example.
Sounds good. Right. So we have. So I guess there aren't any more questions. I'll just check chat one last time. Okay, I think we are good then. So now that all of us are clear on what this algorithm is doing, and again, if something is unclear or if we need to refer back to it, it's right here, it's right next to our working board. So we can always keep coming back to it. And what I'd like to do now is we'd actually get into an example where, again, we have our input trace. We have some space here for being the Sieve policy ourselves. We'll do it by hand and we'll actually see what the miscount is. So without any further ado, let's actually get into it. So what I'll do is, okay, so we started the first element, which is number 7. So you can see that our cache is completely empty. There is nothing in our cache right now. And as the algorithm says, right, if there is no item in our cache, that is, if the length of our cache is not C, it's not full, we can just insert the item into the head of the cache and we move on, right? Very simple. So what I will do is I will insert 7, and you would have noticed I copy pasted a rectangle over here. That rectangle is mainly for the visited bit. You can see here on line 16 that we need to mark the visited as 0, correct? So all that I'm doing is I'm just going to write here 0, just like what the algorithm tells me to do. So on line number 15, it tells me to insert the item at the head of the queue, which I have done. 7 is at the head. And on line number 16, it tells me to mark the visited as 0. And I have done just that. So let's move forward to the second item in the cache, which is 7. I'll also update the miscount as I go along so that we are not clumsy later with our counts. Let's have accurate counts so that we can definitively prove that this sieve is better. So we had a miss because initially our cache was empty. And now we come to the second item in our trace, which is 7. And as we can see, 7 is there in our cache. It's right here in the beginning. So we need to mark visited as 1. You'll see that on line number 2 in our algorithm. So I'm just going to do that. I'm going to mark it as 1. Easy. The next item in our cache is 5. So 5 obviously is not in my cache. So as you would all expect, it's a cache miss. So to do this in a disciplined way, I'll increment the miscount. So now we are at 2. And we need to insert the item at the head of the cache and we can do it because we have free space. You can see we have 3 empty slots over here. So I'll do just that. What I'll do is I'll move 7 to the right. I need to move it to the right to create that space. So I'll just do that real quick. So we have 7 over here, and we need to insert 5 at the head, right? So I'll put 5 over here. So as the algorithm says again, I've inserted 5 at the head of the queue, and I have marked its visited as 0. Nice and simple. Now we move on to the next element in our trace, which is again 5. So I will mark it. So I will mark the visited bit as 1, just like the algorithm tells me on line number 2. I've done just that. Now I come to the next item in my trace, which is 6. So 6 is not there in my cache, unfortunately. So it's a miss. So I will increment my miss count. That's the first thing I'll do. So we are at 3 misses now. And what I will do is that my cache has space. It has 2 empty slots, 2 nice and empty slots, which I'm going to be using. So what I need to do is I need to move 5 and 7 to the right and then insert 6 at the head. So I'll just do that real quick now. So 7 moves 1 space to the right. 5 also moves 1 space to the right. And now I will insert 6 at the head. So 6 is over here, and its visited bit is going to be set to 0, just like what line number 15 and 16 will tell me. Now I move on to the next item, which is 10. 10 again, same concept. I have some space in my cache, so I'll just take it in. So I'll move 7 over here. I will move 5 here, and I will move 6 over here, and I'll keep 10 over here, and I'll mark it as 0. So what we see here is that we have inserted 10 into the cache at the head where the algorithm tells us, and we have its visited set to 0 because this is newly inserted into our cache. And now things will get interesting for the remaining 4 items of our cache. For people who have been thinking that till now things are a bit boring, things will get interesting now for the last 4 items because now our cache is full. So now we'll have to evict items. So let's get into that real quick now. So the first item is 9, and we can see that 9 is not in the cache. So we need to increment our miss count again to 4. And I think the miss count, wait, have we missed something? We had 7, 1, 5 is 2, 6 is 3, 10 is 4. Okay, 9 is 5, yeah. I wish this would not happen on live stream, but okay, it's 5 because for 9 we have a cache miss again. So we had 1 cache miss for 7, we had 1 cache miss for 5, we had 1 cache miss for 6, 1 for 10, and 1 for 9. So that gives us 5 in total. So we are at 5 cache misses now, and we need to find space to insert 9. So to find that space for 9, I'm going to do exactly what the algorithm tells me. I will start at the tail because the hand has not moved at all till now. It's stuck at the tail. I'll start at the tail, and I'll see if an item has the visited as 0. And if the visited is 1 instead, I will set it to 0. So you can see that for 7, the visited is 1. So what I'll do is I'll set it to 0 because on line number 9 you can see that it's telling me that if visited is if the visited is 1, I set it to 0. Then what I do is I move to the next item in my cache, which you can see here is 5. Same thing, the visited value is 1. That's line number 8. Line number 9 tells me to set it to 0, so I will do just that. And then I need to move to the next item in the cache, which is 6, right? Now the interesting thing is for 6, the visited value is not 1. So line number 8, the while condition is false now, right? Because the visited is 0. So what I will do is I will come out of my while loop, and I will discard this item. I will remove 6 from my cache, right? I will remove 6 from my cache. So I will do just that by deleting it. So 6 is gone, and the hand has to move to the next item. So you can see that on line number 13, p is equal to o.previous. So that just moves it to the next item on the left, which is 10. So what I'll do is I'll just clean this up a little bit, and I'll move this over here. So this is how our cache looks right now. And on line number 14, which is the last line or the last few lines, we need to remove the item which we have done. Line 15, we insert the new item, which is 9. So I'll just insert 9 now. So I'll just take this. I'll put 9 at the head of the cache because on line number 15, people with keen eyes will notice that you need to insert X in the head of the cache. So line 9 goes over here and the visit is set to 0. So I'll just delete these links because we don't need this right now. Right. So this is the current state of the cache after dealing with element 9. I just want to pause here again just for a few seconds if anyone has any questions on what we did. I just want to pause here simply because this is where we really did the Sieve algorithm's secret sauce, right? The hand and searching through the items and seeing where visited is 0 and so on. I'll just pause here for a few seconds. If anyone has any questions on what we did, feel free to ask. Right, I'll just check chat one more time. Okay, I think we are good and everything's clear. So that's great. And yeah, thanks for the reactions with the emojis. Please do that if these questions come along. It helps me know that everyone's on track. So right, we are done with item 9. So we can move forward to the next item in our trace, which is 1. 1 again, we can see unfortunately is not in our cache. So we need to increase the miss count. So the miss count has now become 6, right? Now we need to find some space for item 1. And this was a question that someone even asked just a few minutes back when we were talking about the algorithm, which is where does the hand go? So the hand never resets to the tail. The hand just continues from where it was the last time. So you can see here that the hand had stopped at 10. And now we are going to start our scan also from 10. We're not going to restart from the tail. We're just going to start or we're going to continue from the tail. Sorry, we're going to continue from 10. Right? We don't reset to the tail at all. We just continue from 10, which was where we last left off. So as you can see, this is kind of a slam dunk, right? We were literally sitting on 10 and the visited for 10 is 0. So we can instantly remove 10 from the cache. We don't have to even move the hand forward. We can just remove the item that we are sitting on. So we just remove 10. That's it. It's gone from the cache. I'll just quickly clean this section up. I'll move 9 here. And now what we need to do is we need to insert 1, right? That was the incoming item. So I'll just do that. So take this, put this over here. And the item 1 is inserted with the visited as 0. Perfect. So we have inserted 1 into the head like the algorithm tells us on line number 15. And we are good now with item 1 as well. Now the last 2 items of the trace, we're almost there.
One
Oh, sure, go ahead.
question here. So in this case, hand should also move one step back, right? Because of p is equal to o dot previous.
Okay, so this is the interesting part in the paper that previous actually means forward towards the head. It doesn't mean towards the tail. So this is something which tripped me up also. But you can see it in the algorithm. We never use o dot next. It's always o dot previous.
That's fine, but let's say that 4 nodes that we have in our linked list, the hand should move to the first node, right? And when you removed the last element.
Oh, sure. I can probably let me undo it. So we had, yeah, so it was like this and we removed 10.
Yes.
Yeah. So, okay, let me go through the steps step by step. So we were on, so we start on line number 13 because we have come out of the while loop. So what we do is we say p is equal to o dot previous. So o dot previous is the next element, the left element. That's how they do it in the paper. So what happens is that if you want to talk about p, right, p would be this. I'll just remove hand and I'll call it p. And basically this is o. Let me even call it o. So line number 13 is done. P is equal to o dot previous. I will now discard o because that's what the algorithm says on line number 14. Gone. And obviously, because we're deleting from a doubly linked list, the connection is done this way.
I see.
Yeah,
Okay.
and then we insert on line 15. Yeah.
Got it. Understood now. It's because of the new head is being inserted, so that's why it's again on the second node. Our hand is on the second node.
Yep, that's exactly the reason. And yeah, okay. So wait, no, this should be 1. Yep. So that's the reason, and that was a really good question because In the visualization, I see the hand doesn't move that much. The hand is pretty much staying where it is, but the data around it is moving because you're deleting from the linked list. And this is also an interesting reason why you should use a linked list for this application, because if you use an array or a vector, like in certain languages we call it, what would happen is you would have gaps in your vector or your array. And we all know that when you have these gaps, you have to sort of move data around. You have to kind of push data around left and right. And that is expensive if your cache is large. But with linked list, it's very simple. You just delete that node, you do a bit of pointer manipulation, you're done. Your list is clean again. So that was just a small plug on doubly linked lists. So yeah, last two items, we're almost done with Sieve. We have number 5, and number 5 is in the cache, so no problem, no misses. We have visited as set to 1. And the next item, the last item, is 7. 7 is again a cache hit, so the visited is set to 1, and we are done. The miscount doesn't increase. So the final miscount that we have for Sieve on this trace is 6. So I'll just mark this in green so that we know we are done with this. And this is the Sieve algorithm in action. So this is how we run it, whether it's a cache hit, whether there was free space in the cache, or if we had to evict something. We did all the cases. Now, what I'd like to do is I'd like to do the LRU algorithm also real quick so that we can see how it compares to LRU. So in LRU, as we all know, in LRU you can maintain a queue, and the idea is that anytime an object is hit in the cache, that object moves to the head of the queue. And whenever we have to remove an item from our cache, we have to throw something out to create space essentially, we remove it from the tail. So you can imagine that the popular items or the least recently accessed items are at the head, and the items that have not been accessed for some time, they are kind of old, not very popular, they are towards the tail. So the tail is the perfect place to remove items from. And we'll see that in action now real quick, and we'll see the miscount. That's the main part I want to speak about for LRU, the miscount, and that it's more than Sieve. So we'll do that quickly now. So again, we'll take our trace and we'll start from the top, which is 7. 7 is a miss because our cache is empty. So the miscount is becoming 1, and 7 is at the head. Then the second item is again 7, so there is no cache miss, and 7 remains at the head of the cache. Absolutely fine. Then we have 5, which is not there in our cache, so it's a cache miss. So our cache miss count is going to go to 2 now. And because the recently accessed items have to go to the head, because that's where the popular items are, 5 is at the head because it's the most recently accessed item, and 7 moves 1 position to the right, closer to the tail. 5 again, no miss, it's at the head of the cache and it will stay there because it's the most recently accessed item. 6, cache miss unfortunately. We need to increment the miss count, so that becomes 3. And we need to insert 6 into the cache at the head because it's the recently accessed item. So I'll move 7 here, I'll move 5 here, and I'll put 6 over here. Then we have 10, again a cache miss. So we increment the count again to 4. And yeah, we move 7 to this side, we move 5 over here, we move 6 over here, and we move 10 to the beginning, because 10 was the most recently accessed item. Now we come to 9, and now things get interesting. When we come to 9, we need to remove some item from our cache. And as discussed, the least recently used algorithm will use the item that has been used, like the oldest item, the item that was not accessed for a long time. And that was 7, because 7 has not been accessed for a long time and it's been sitting in our cache. So it's time to throw it out. And that's exactly what happens. So we move 5 here, we move 6 here, we move 10 here, and 9 comes to the beginning. Now keen observers here will notice one interesting thing. We just threw out 7 from our cache. But if you look at the trace, we are going to be accessing 7 again at the end. So LRU has actually made a bad choice here. Again, we are looking into the future, but it's an interesting thing to note that LRU has actually made a bad decision here. It's thrown out 7 when it's going to be accessed in the future. So just keep that in mind as we go through the remaining of the trace, how that affects the miscount later. So we'll move on now to 1. Again, it's a cache miss, so we need to remove the oldest accessed item, which is 5. So we have 6 here, we have 10 here, we have 9 here, and we have 1 over here. Miscount has obviously gone up. It's gone up to 5. And again, keen observers will notice we threw out 5 from the cache. And 5 is the next item we are going to access. So we just again made a bad decision with LRU, right? So this is going to hurt us now, and you'll be seeing this in a moment. So we come to 5. And in case of 5, it's a cache miss, unfortunately. So we have to again remove 6, because that's the least recently accessed item. Then we move, okay, wait. Yeah, so yeah, 6 goes out. So we have 10 over here. We have 9 over here. We have 1 over here. And we put 5 over here. So this was a miss. So this makes our count to 6. And finally, we come to 7. Again, that bad decision that we made earlier is coming to hurt us back. And we again have a cache miss. So this is 7. So you can see here that this will be 9, this will be 1, this will be 5, and this will be 7. So you can see here that because we threw out 5 and 7, because of some random items in between, 6, 10, 9, 1, right? Because of 6, 10, 9, 1, these randomly occurring items in between, we threw out 5 and 7 from our cache. And that hurt us later, because when 5 and 7 were accessed again at the end, we didn't have them in the cache. So we had extra cache misses. So you can already see here that LRU is worse. And I will pause here for a second just to, if anyone has any questions. The main point here which you need to take away is that in case of LRU, certain items which were popular just for one access, 6, 10, 9, 1, they were only present once in our trace. Just because of them, we removed actually popular items. Look at 7, look at 5. They're accessed so many times in our trace, but still they were thrown out. But in case of Sieve, we didn't do that. We kept those items in our cache. So that's the main observation I want to drive home with this example. And if you have any questions, anything was not clear in the example, feel free to ask. I'll wait a few seconds now. And as usual, if things are clear, things make sense, feel free to react with your favorite emoji on the Discord system. It gives me a good idea if people are following along. Perfect. I think we are looking good. I don't see anything on chat as well. So that's really, really good. So that's the case with LRU. And in case of FIFO, things actually get a lot worse. So what I'll do is, for the interest of time, I will come back to FIFO later, probably in the other session. But the one thing about FIFO is that it's even worse than LRU in terms of performance, because in a FIFO cache, what you actually do is you don't track any item in terms of usage, or in case of cache hits. So what would happen is that you would put 7 in the cache. You would put, wait, maybe I can do this real quick, because FIFO is like super simple. Maybe I can actually make it happen in just a minute or so. Let me take this. Oh no, I don't want to put text on that. I just need the arrow. Yeah. Okay, so there we go. Right, so let's do this. So we have 7. So that's a cache miss, number 1. Then we have 7 again, no problem. It's a cache hit, so we don't do anything. 5, again, it's a cache miss, so we need to increment our count. And what we do again, because it's a FIFO, it's a first in, first out. So we need to insert items. Okay, normally items are pushed towards the tail. That's how they always do it in these simulators. So I'll put this here, and I put it at 7. Then the next item is again 5, which is a cache hit, so no problems. 6 is again a miss, unfortunately, so we need to have a cache miss here, and we need to put it in our cache. So we get 7 over here, we get 5 over here, and we put 6 over here. Then we move to 10. Again, it's a cache miss, so we increment our count to 4. And we need to create now that space for 10 to come in. So I'll just do that real quick. 10. Then we come to 9. And again, people will see the same problem that LRU had. They're going to throw out 7 again, which is again a very bad thing to do, because we'll need 7 very, very soon. So 6, 10, and this is 9. So we increased our miscount. Now we come to 1. Again, it's not in our cache. We need to increment our miscount again. So this will be 6, this will be 10, this will be 9, and this will be 1. Now we come to 5, and again, our bad choices have come to haunt us back in just a few item accesses. We can see that 5 is not in our cache, and we need to pay for that price. So we need to actually increment our miscount to 7. So we have 10, we have 9, we have 1, and we have 5. And finally, the last item access, again, we're still bruised and it just keeps hurting again. Another miss. So we have 8 misses, literally. So we have 9 here, we have 1, we have 5, and we put 7 back in the cache. So you can clearly see that if LRU wasn't bad, FIFO is much worse. And Sieve does much better in these sort of workloads. And these are like web cache workloads where some items are very popular, and then you have this random noise coming in between, which is not popular at all. It's just random noise accesses in between. Someone randomly access some data out of the blue, and that kind of messes your cache up in terms of LRU and FIFO. But Sieve is like resistant to it. It knows that many items may come in, but they are not popular, so they can be thrown out very quickly. But there are some items, just a few, which are popular and which must be retained in the cache for a long period of time. And in our case, in our trace, that was 5 and 7, and Sieve does a very good job at that. So that covers the entire example, the trace, the hands-on, and kind of driving home that point of why Sieve is better. So one last thing that I want to cover for today, I know we are a bit over time, but I want to cover this because this will kind of allow all of us to sleep better at night, because we'll know why Sieve is doing better. Like, why is it that in this workload, Sieve is actually performing well? It's beating LRU, it's beating FIFO. Why is it so good? So the reason why it is so good is mainly because of two properties that I spoke about earlier. There was a question about this as well. So I want to answer that question now with some detail, which was about lazy promotion and quick demotion. So what this concept means is that we'll take it step by step. Let's first talk about quick demotion. I feel this is easier because we saw this happen a lot in our example as well, right? There were these few items in our trace which just came in once and they never came back again. But they had a devastating effect on our cache. We lost some items like 5 and 7 which were very popular. So the interesting thing is that the Sieve algorithm recognizes this problem and addresses it in a very simple way. It says that items which are put into the cache must be removed quickly as well, unless those items are accessed often. So in our case, in our trace, if you recall, items like 6, 10, 9, 1, these were just accessed once and they were never accessed again. So the Sieve algorithm very correctly says that no, these items need to be thrown out quickly. And items like 7 and 5, which were accessed quite often, these remain in our cache. So that is an important concept that the Sieve algorithm uses. And this is very specific to web caches. So you can imagine any website, Twitter, Facebook, they all have this sort of workload. And to give you an intuition of this, imagine a famous celebrity. They tweet something. Now, their tweet is a very good thing to cache because people are going to access that tweet like anything. It's going to get millions of views. People are going to be reading it again and again. It's going to get retweeted. It's going to get liked. People are going to quote the tweet. A lot of things are going to happen. So that is a very good item to cache, right? But then there are tweets from accounts which are not as popular, right? Those tweets are not going to be accessed as often. They might get 100 views, 200 views, maybe over days, not even in an hour. They're going to get it over days. Not many people are going to access it. It's going to quickly fade away. Those tweets will be created. They will not be there in the cache, but no one's going to access them a lot, right? No one's going to ask for this user's tweet. They're not very popular. Their tweets are not going to be very popular. So because of that reason, those tweets can be quickly removed from the cache to make space for these very popular tweets from celebrities or people who have a lot of followers. And this is what quick demotion boils down to, that there are going to be many items which are not popular. So don't bother keeping them in the cache for long. But there are going to be some items which are very, very popular. So you need to hold on to them in your cache. I will pause here for a few seconds. Anyone has any questions on quick demotion? Anything that didn't make sense or the example, let me know. Right. I think we are good on quick demotion then. That's really good. The next one is lazy promotion. So with lazy promotion, the concept here is simply that when an item comes in your cache and it's being accessed multiple times, right? It's a popular item. Don't immediately take it to be popular. Have that sort of suspicion. That's essentially what lazy promotion is saying. So a simple way to understand it is like this. If we go back and we look at what LRU used to do, right? You would remember that what LRU was doing is that if an item was accessed, it would move that item to the head of the queue. It would move that item to the front of the queue because that item was popular, right? So you can see in this simple example, you have A, B, C, and B is in between. And the moment B was accessed, it became a hot item. It became a popular item. So what we did is we moved it to the front of the queue. That's what LRU does. But this is not a good idea. And the reason is because items which are popular, you need to be skeptical about it. You can't just immediately say, oh, an item was accessed, say 3 times. It's going to be popular in the future. No, you need to wait a little bit, see the access over some time, and then decide if you need to keep the item or not. And the way Sieve implements this concept, which I said, is by having that visited bit. That visited bit is literally what is used for the promotion concept, because if an item is popular, that bit will be set, and when the hand scans that particular item, it will see if the bit is set or not. If it is set, all good, the item remains in the cache. If it is not set, if it is 0, that item will be removed from the cache to create space for an incoming item. So that is the main concept in terms of lazy promotion. And again, there are a few good side effects of lazy promotion as well, which is that when you do lazy promotion, right, all that you do is you just set a bit. As I mentioned, right, you just go there, there's this visited bit, you set the bit and you're done. That's it. That is very cheap to do computationally because you are just setting a single bit, very, very cheap single CPU cycle and you're done. And also, it's very quick to do. You're just accessing an item and setting a field. But in LRU, look at what you're doing. You're removing an item from the linked list. You're inserting it again at the front of the linked list. Imagine all the pointers that you need to modify, right? You need to change these pointers, put it at the beginning and so on. And that makes it very computationally expensive, especially when you imagine multiple people accessing the cache. So everyone's accessing the cache, playing around with pointers. It's a very very uncomfortable scene because things can go wrong in so many ways. And Sieve completely avoids this problem. So this was mainly the concept of lazy promotion and quick demotion, and why it makes Sieve perform so well on web caches. I'll pause here for a few seconds again. If anyone has any questions on what we discussed, feel free to unmute and ask or put it in chat.
We have a comparison of Sieve against LFU as well. I mean, the most famous algorithm which it comes close to this implementation might be LFU, in terms of they both consider accessibility and the number of times the key was accessed. So how does it fare against LFU?
Right. So, okay, so in terms of LFU, okay, so for those who are not aware, LFU means the least frequently used. So the idea in a least frequently used approach is that any item which is accessed the least amount of times is the item which is good for eviction. So the problem with LFU is that in LFU, the item that you evict is almost always going to be the item that was just inserted into the cache. And because simply, I mean, the reason for that is simply because the item which is just inserted into the cache is the least frequently used one. It was just accessed once and now it has been put into the cache. The problem with that is that you're not giving enough time to these items to, you're not giving any time for these items to prove if they are hot items or not. Like, for example, if I take the celebrity case again, right? When the celebrity tweets their tweet, right? That time 0, that T0 when the tweet just happens, that item will be in the cache, 100%. But in an LFU policy, it's possible that that tweet from that celebrity might be removed instantly from the cache because that tweet is brand new, it's just entered the cache, and because some person with less followers has put a tweet out to create space in the cache, the celebrity's tweet has been removed. and that is something that is guaranteed to happen in case of LFU. But in case of Sieve, there is a hand, I do agree, there is a hand which scans the cache for a free space, and the celebrity's tweet also will have visited as 0 when it enters the cache. But it's not guaranteed that the celebrity's tweet will be removed immediately, right? If we look at the example that I just showed, you'll notice that the hand is never on the incoming item. In the sense, whenever I inserted an item, the hand was never on that exact item, right? There was always some buffer. And that gives that item some time to show that it's popular or not popular. So that buffer space which Sieve provides makes it much better in web cache workloads compared to LFU. I hope that makes sense with the celebrity example. Let me know if you have any follow-up.
It does actually. I mean, it sort of adds a bit of a randomness into, let's say, which element should be removed amongst the least frequently accessed elements. So yeah, sort of makes sense. Yeah, I got the gist of it.
Sounds good. And this is something which even the authors touch upon in the paper, that because they're sequentially scanning the cache again and again, and again, they're not resetting back to tail, they're just picking up from where they left. A very beautiful thing that happens is the items that are on the right of the hand, which is the stuff over here, tends to be the items that are older in the cache. That means they have proven that they are popular. And the items which are on the right of the cache are items which are yet to prove their popularity. They have a chance, they do have a chance to prove their popularity. They won't be thrown out immediately like LFU, but the chance of being removed is higher, is all I will say, but not immediate.
Yep.
Sounds-
Definitely. I think yeah, it's like most frequently accessed elements might be on the right.
Mhm.
Recent elements would be on the left, and what we want to remove is actually somewhere in the between. So I think that's the idea what this algorithm sort of targets upon.
Exactly, and the hand plays a separation point in that design. Yes.
It's a very, very elegant and very simple algorithm. I mean, it's actually very beautiful in a way. Really nice.
True. That I really like this algorithm for that reason, because I think for people who even joined in, and I know some people dropped because we are overtime. I again apologize for that to everyone. But the interesting thing about this paper is that it all boils down to just this 16 lines of code, and that's it. You can literally forget about the rest of the paper. Just implement these 16 lines in your favorite programming language, and you're good. You have Sieve. If it matches your workloads, it's going to be very beautiful in terms of performance and efficiency, and it just works really great. Right. I While I'm waiting for any more questions, I just want to see my whiteboard. I know we are over time, so I won't cover much more today. I will keep stuff for the second session when we have the live coding. Because live coding, Sieve, again, I'm sure many people would understand now that it won't take more than say 10 to 20 minutes to do the entire coding and testing and benchmarking to see how good it is. So in the next session, when we have that spare time, because every session is normally an hour long, in that spare time, I'll cover the concepts which I could not cover today, like limitations. There is a small mathematical derivation which I've taken the time to break down. So don't get scared by these symbols. Please don't. Don't have any nightmares. It's a good weekend. But I've broken it all down so that you can understand it piece by piece. Mainly, this math is just to prove that Sieve will remove items that are newer. That is the lazy promotion I was talking about in the quick demotion, and that it gives the older items a longer time in the cache so that they're popular. So this is basically the math that they have given to prove that, which I will also be explaining in the next session. It's all in the whiteboard. Just needed to have that time to explain it. Limitations I already mentioned, and yep, I think we have covered most of everything else. So I'll just wait now for a few minutes if anyone has any questions, or I just want to talk a little bit about the paper or anything that they have. And the rest of it, we will cover it in the next session for coding, because we'll have enough spare time there. And I'll put up a poll for that session soon. And yeah, if any questions, anything, we can open the floor now.
Yeah, hi.
Hi.
So this Sieve kind of mostly seems suitable for social media apps. right? Uh, can you give any use case where this might not be a proper fit in the architecture?
Right. So that's a very, very good question. And the answer to that is actually in the limitations. Let me go down there for a moment. Over here. Right. So I'll give a quick overview of this. So mainly the idea here is that when we talk about web cache workloads, right, as I've been alluding to throughout this discussion, there are only few items that are very popular. There are those few items which get a lot of requests, right? Like the celebrity tweet example I gave. And there are going to be a lot of objects which don't get a lot of requests. So this is kind of the distribution, as you can see in this image on the bottom left. I'll just zoom in a little bit more. And this is the type of workload that Sieve is optimizing for. And now the problem comes that when you're optimizing for a certain type of workload, there are going to be other types of workloads where you won't perform as well because the assumptions you're making won't be true. So to give you a better example of that, a big problem with Sieve is that it is not scan resistant. So what does scan resistant mean? I'll explain that now. So normally what happens, especially in CPUs, like in terms of your operating system, your local system, right? What tends to happen is that you have workloads where you're not creating a lot of items, right? It's very rare for any of us to create 100 files every day, every hour. Very, very rare. And it's also very rare for certain items to be extremely popular compared to other items. It's normally a much more balanced access. So imagine your own computer, right? There are some files that you access on certain days. Sometimes you never access them once you're done with them. You don't create a lot of files on your system every day. It's only 1-2 files and that's it. Normally it's you're accessing existing files. And that type of workload doesn't work well with Sieve, because in these type of workloads what you're doing is say you're opening a file, you're scanning through the file, that is you're scanning through the bytes of your file and you're loading them into memory, and this can happen very sporadically. And in these cases what tends to happen is that the Sieve cache, just like how we saw LRU, where the LRU cache kind of messed up and threw out important items, Sieve also will start throwing out important items from your cache, because what will happen is that it'll get a lot of these random file accesses happening on your system. It will try to find free space, and in trying to find free space, it'll have to evict the popular items because it has to create space somewhere. And in that case, you'll have a lot of cache misses. Let me know if that makes sense. I can even give another example if you'd like.
I kind of understood, but I mean, let's take an example. Every day, mostly I'll be with my laptop. I'll be using text editors, IDEs, browser, etc. And I would rarely use other apps like maybe the app to change wallpapers or something. So doesn't this also seem a better use case for that? I mean, we even in uh, our laptops as well, we'll be using very less set of apps which will be used frequently.
Right. Okay, that is a good point. Now, the one interesting part there, which you brought up, is that when you look at web cache workloads, right? I'm not sure if I mentioned this when I was talking about the metadata usage. But the thing is, in web cache workloads, normally the data that is there is just in tens of bytes large. That's it. That's the size of the data that you're holding. And you can imagine that if you have a cache, say, of 1 GB, right? You're holding all these items of 10, 20 bytes in web cache workloads. But when you look at your local file, your local computer operations, right? You open a file, you access a PDF. I'd like to say this as a shameless plug. You open my whiteboard, anything like that. It's a lot larger. There are a lot of more bytes coming into your cache. And when you have much larger items like these, what happens is this property, which the authors even quote in the paper under limitations, is that you have this property where you're scanning multiple blocks. People who know OS will know this, right? You have pages, you have frames when you're reading from your storage. So what you're going to do is you're going to read a lot of bytes from your storage for all these things. Say you're accessing a website, it's going to be a few megabytes at least, not even including the images. You access a PDF. Normally PDFs also today are 20, 30 megabytes at least. All of that needs to fit in your 1 GB cache. And very quickly your cache can get overrun with all these items. And the main point which I want to draw home, and I hope I get this point clearly across, is that you have a mix now of popular items, which are items which have to be in your cache, just like what we saw in the Twitter example, the popular celebrity example. And there are some items which you just open once in a while, right? You'll have a mix of these now in your cache. And what tends to happen, especially when you have these larger files and all these things locally, your cache tends to get overrun with these new items because there's just not enough space for the older items. So because of that, to create that space on your system, these older popular items also have to be evicted. An example just clicked in my head, which I think I can explain this with. Say that you say that you're using Chrome, right? You're using Google Chrome, and say that you have a few favorite websites. So you have YouTube, you have Twitter, and say you even have your email client, right? Those are your 3 favorite websites. Now, what is going to happen is that those are not the 3 tabs, if I can use that term for browsers. Those are not going to be the only 3 tabs that you have open on your system, right? You might have tabs open on a blog post that you're reading. You might, which again, you'll just read once and you may not read ever again. You might have a tab open for maybe some other websites which are not as popular in your use case, but they're open right now. And normally what happens is that those tabs are a lot more, right? You might have 10 or 20 tabs open on your system, and only in my example which I gave, only 3 tabs are important to you: your Twitter, your email client, and YouTube. Now, if your cache is not large enough, these new items which have come in, which again, as I mentioned, these your blog post or anything like that, those have to also be fit in your cache somewhere, right? Like I showed, whenever there's a cache miss, it has to be put in your cache first. So because of that, these incoming websites which you access very less frequently will now fight for space in your cache. And who suffers? These popular items. I hope that makes sense. Let me know if that example, the browser example, clicks.
Yes, yes, that clears my doubt.
Perfect. That was really good. That was really good
Thanks.
question. Thanks.
One more thing that, let's say, in terms of eviction
Mm-hmm.
performance as well, this will be slower than the popular algorithms, right? Like LRU and LFU, because it does a linear scan and then it decides which particular element to remove. So there would be some latency because of that as well, right? Which can result in certain use cases where this might not be useful.
Correct. So again, that's a very good question, and my answer to that would be mainly the amortization property, which is that it's not going to be always the case that um, that you have to do an O of n scan to find a empty space in your cache. So what tends to happen is that the cost of scanning will get amortized over multiple accesses. And another interesting property that I want to add here is, even in case of LRU, right? Um, in practical terms, the pointer manipulation also is quite expensive. So again, I know in asymptotic complexity this does not get reflected very well, which is quite unfortunate. But even in case of LRU, the fact that you have to do all that pointer changes, and again, caches today are very multi-threaded. Every request will share a common cache. Doing that pointer manipulation when you have shared caches is again a pain. You have to lock, you have to either use atomics or something, um, and it's a very difficult to get right. And even when you get it right, it's quite slow because all the threads have to synchronize with accessing the cache and so on. So in that practical term, which I think I mentioned here, I think I mentioned it under scalability. Sieve doesn't have that problem. It doesn't need the locking to happen because it doesn't do any sort of pointer juggling. So it's much faster that way in practical terms with multiple threads and so on. And yes, the amortization property.
Yep.
Yep, makes sense. That answers my question.
Perfect. Sounds good. I know we are down to a last few people today, which again is completely valid because we are over time now. I just wanted to know from everyone here um, about today's session, and even I see some familiar faces here from the nanolog session. I just want to get some feedback on how the sessions are going, if there's something more you'd like to see um, going forward, or any changes in the whiteboard style.
Nothing from my side, to be honest. I think it's pretty much perfect. And the Nellog also is very good, and this is also going very great. So yeah, thanks a lot for doing this, and this was generally a very good session. No feedback.
Oh, perfect. Thank you so much. I even see the Discord reactions. It means a lot going through these sessions. I know that Saturday evening is a very, I would say, very sacred time to everyone, whether it's getting out from university or from office work. And the fact that you come here to spend to learn and interact with everyone means a lot. And I think, yeah, for me, it's a competition that I need to make that time worth it. With that, I think we are good for today. Covered a lot of things, learned a lot of stuff, saw a new algorithm which can really make certain workloads much better with caching. If anyone has any last questions, comments, feel free to unmute and chat. For everyone else who has to leave, thank you so much for joining. It means a lot. And we'll meet in the next session where we implement Sieve and we see the last bits of its limitations and the math which I spoke about earlier. Thank you all so much for joining. If anyone wants to stay back, chat, I'll be there here for a few more minutes. And after that, we'll call it a day.
Any concrete places where this is being used right now?
So Sieve, interestingly, has been implemented for many popular caching libraries. The authors have mentioned they've used it across popular libraries for Go, Rust, Python, I think even C++. So they haven't name dropped any companies that are using Sieve at the moment, unfortunately, but I believe that anyone who's using these caching libraries can literally switch on using Sieve with just a few configuration changes. And I wouldn't be surprised if people are using it today, because for web cache workloads, it really is very good. It's simple, so people in production won't be scared to put it into production, and it scales quite well, which fits a lot of web scale use cases. But I think maybe to make this answer a bit more interesting for the next session, let me try to figure out if someone is using it. Maybe some tweet, some blog post by someone who's talked about them using it and getting some good results. Let me see if I can fish something out for the next session. I'll keep a note of this.
Sure. Even I was trying to do the same right now. So let's discuss about such implementations and such the next session.
Sounds good.
Also, this seems like a relatively new algorithm being published in the research paper. Like I have seen the what do we say? These references taken by the research paper. Most of them are very recent, like 2023 also. So we may not be able to find too many what do we say? Like the companies or others using this right away.
True, that is a good point. I'm sure many companies will still be reading the paper and probably trying stuff in their dev clusters. Like people in industry will know
Yeah.
that there are these things called dev clusters where you try out things, and if they are working fine, you put them into production. And I'm pretty sure that people are either evaluating it or there might be some early results. But that's a very good point that given it's so new, I think people will still experiment with it before putting it in production. But let's see if we find something, because I'm sure there'll be a first mover somewhere.
Yeah.
And I think one other point again on that question was that this paper is quite recent. It came out in 2024 as part of NSDI, which is a Network System Design and Implementation Conference. Again, very popular, very highly rated. is again by Usenix, which is a association who's for another conference we saw in Analog. So very prestigious conferences. So this is some real core stuff. So yeah, let's see how this goes. But no matter how it goes, we now know the algorithm well.
Is there a way to share this the diagram draw.io?
Oh yeah, definitely. So maybe I can spend a second on that. So I do share these whiteboards. I think, yeah, this is actually the one that, this is the repo that I've been maintaining. Let me share that in chat. I've just put the link in chat now. So this is the repo, and people who missed Nanolog or who want to see the whiteboard for Nanolog, it's over here. If you hit the Nanolog folder, it takes you to this image. So you can see it in all of its glory. So this has everything we covered in Nanolog as well. People may remember certain parts of this, the quiz on %n, the compaction scheme and how smart it was, the limitations, and so on. And I will be uploading the one for today's session, which is Sieve, soon this weekend, so that everyone has access to that. And yeah, this is the repo that I'm using throughout to maintain everything that we discuss. Even the implementation of Sieve, which I'll be doing in the next session, I'll be uploading it here.
Okay, thank you. Thanks for doing this. It's
Okay.
really
Oh, thank you so much. It means a lot, the support, because it means a lot.
means a lot.
Yeah. Cool. I think we are at 9:35. I guess it's, yeah. No matter how sad this feels, it's time to call it the end of today's session. Thank you all so much for joining. If you have any, again, questions, comments, suggestions, feel free to put it in the Discord channel over here, or even share it on DM. I think my Discord DMs are open. Someone had told me they weren't earlier, but I've fixed that problem now. So feel free to message me there if you have any questions or suggestions. And yep, we'll meet soon in another session. Thank you all for joining. Have a great evening. See you later.